Okay, I want to go over the most basic type of calorimetry problems with you so you can see which way we can go with this calorimetry equation. Because there's really only a couple of types. So if you get these down, you should be in pretty good shape. The general idea is that one body gives off heat and another one absorbs it. Now this negative sign, technically it doesn't matter where you put it. It doesn't have to be with the exothermic one. If the water's losing heat, we could put it over there too. So that doesn't mean that this is always exothermic, but this is what happens. We have a heat transfer. Okay, so one very common type of problem is the heat, specific heat of a substance. So if we calculated the specific heat of water, we could find the heat of the water and therefore change the sign, and we could know the heat of the metal or the unknown or whatever it is. And then we could calculate one of these variables of our unknown. Okay, so we would know the water, and then we would know this and be able to calculate one of these. So this is a pretty straightforward, this is the most straightforward one because we would have all of the water information and it's a quick transfer over to here. The second one is very similar to this, but when the variable is what is the final temperature, you can't just calculate one and plug it into the other equation. You actually have to set them equal to each other the whole time. So we have to expand both of these and say the mass of the unknown, and we need that negative sign distributed everywhere. That's a really common mistake. The specific heat of the unknown, and then we'll say final minus initial temperature equals the mass of the water, specific heat of the water, and the final minus initial of the water. Now, in this scenario, we would have all of the variables except the final temperature. But the final temperature would be the same on both sides because one will heat up and one will cool down. So they're going to solve, you have to combine like terms to solve for that final temperature. This is another type of calorimetry problem, but there's a little bit more algebra here. You have to distribute everything, combine like terms, and solve for the final temperature. So that's another one. The third one is when we get into delta H calculations. Now, if we, the units on this are kilojoules per mole, but watch out, we could do kilojoules per gram too, same thing. If we found the heat of the water, mass of the water, specific heat of the water, this will give us that value in joules. We could easily convert between joules and kilojoules, so don't get lost there. Change the sign, and we could get the heat of our reaction, whatever that is. And then we would just need to know how many moles do we have. And if we just divided those terms, we could get a delta H. Okay. So this is a way to get, maybe this is a combustion reaction or lots of different things. This is a way to get an enthalpy for a specific reaction. How much heat went into the water? And then if we just divided that by the grams or the moles, this is similar to the candle lab that we did. How much heat is in a gram or how much heat is in a mole, you could find the delta H of the reaction. We don't care what the subscripts on this are. This could be reaction, this could be combustion, this could be lots of different things. That just describes what type of balanced equation you have. It doesn't actually tell you anything about the math. Okay. The fourth thing is still an enthalpy problem, but it's specifically for solutions. And there's one change here that we need to be aware of for solutions. We are not calculating the heat of the water like we did in this enthalpy problem. If you're dissolving something and it's exothermic and endothermic, what happens is the salt dissolves and heats up with the water. So it's actually part of the system and the surroundings. So how do we account for that? We say the heat of the solution, not the water, is equal to the mass of the solution. And now I'm going to say the mass of the water plus the mass of the salt. The specific heat, we're actually still going to say that it's water because the salt's not going to change that 4.18 significantly. So MC delta T, we still want the water assumption. This is mostly a water-based solution, but there's a little bit of mass of the salt in here. And then the temperature change, that's just delta T. That doesn't change anything at all. This is the surroundings. We change the sign on this, positive to negative, and then we can get the heat of the salt. Okay? Now, in order to get the enthalpy of the salt dissolving, which is what we're after here, then we would just divide by the moles of the salt, just the salt, not the water, or the grams, if the units were in grams. But the big difference between these two problems is just this mass of the solution, because the salt is both dissolving and being heated up with the water to a new final temperature. So those are the four big types of problems. Two of them use the MCAT equation, and they're really very similar. The only difference is this one you need a little bit of a different strategy if you're solving for the final temperature. And then two of them over here are for enthalpies. This one is very similar to the candle lab we did, and this will be similar to the dissolving salts in a solution lab. But it's just when you're dissolving something, you have to account for this mass over here as well. So those are the four basic types of problems you will see in enthalpy reactions. It doesn't get too much more complicated than that. You need to keep track of grams and moles, system surroundings, and positive and negative signs, and you should be in good shape.